Welcome to the Elevate the Edge podcast. I'm Maribel Lopez of Lopez Research, and I'm joined with my co-host Joe Peterson of Clarify 360. If this is your first time listening to the podcast, welcome. Elevate the Edge is published bi-weekly. The podcast focuses on helping companies understand what edge computing is, how the market will evolve, and what you need to know to build successful edge computing strategies. Show notes and subscription links can be found at elevatetheedge.com/episodes. We hope you'll enjoy the show. Hello and welcome back to the podcast. I'm Maribel Lopez and we are here with Joe Peterson, my fabulous co-host. Hey, Joe.
Happy New Year, Maribel.
And we are elevating the edge. And today we're very excited to be joined by another fabulous technical expert. We have Professor Muriel Medard. She is the NEC Professor of Software Science and Engineering at MIT and the Chief Scientist for Steinway. We're so happy to have you here today, Muriel. You are also a member of the U.S. National Academy of Engineering, a member of the German National Academy of Sciences, Lipodonia, and a fellow of the U.S. National Academy of Inventors. I could go on. There's so many great things that Muriel is working on. But first, welcome to the program.
Thank you very much, Maribel. Thank you, Joe.
And thanks to Joe for finding Muriel. So I'm just going to jump right in and say, can you share some of the work that you're doing and how it relates to edge computing?
Absolutely. So the group that I lead at MIT is the Network Coding and Reliable Communications Group. And I think when we talk about reliable communications, we're really talking about reliable computing. Most of the data that's being transmitted right now is not for communicating in, let's say, an old-fashioned sense of just making a phone call. It's really communicating for a purpose, for a particular function, which is usually very much associated with computing. So I'm usually communicating with applications, communicating with different services, and those services are communicating with the purpose of computing on the data in order to provide something useful to me. So a lot of the work that I do is around doing all of these different functions in a way that's efficient, reliable, timely, secure, and private. And that's really the core of what I do. And embedded in that is also in a way which is sufficiently general to have a real perennity so that, you're not making sort of point solutions, which may work very well, and might be quite valuable in a narrow context, but solutions which have a wide applicability and will be of lasting consequence.
So it's funny, you started with the making a phone call, and I just realized I don't remember the last time I made a phone call because everything seems to be a web conference now, and a good old-fashioned phone call might be interesting. But I really like where you're going with the discussion of we've moved communications from what was a person-to-person voice thing to a person to thing, thing to thing. There's a lot of different dimensions in terms of the reliability, the latency, the amount of bandwidth you need to make different applications and services work. And I think that's at the heart of what we're talking about with a lot of edge computing discussions. And I know that you actually were chatting about 5G communications at one of the MIT Summer Institute programs. And I wanted to talk about, what are you seeing in 5G? Why is something like opening 5G communications important? And how does it matter in the realm of edge computing?
Yes, thank you. That is definitely one of the topics that's been, I think, of most interest to me, certainly personally, but I think has been emerging as a topic that really needs to have much more attention paid to it. I'm going to start by latching onto two things you said, Maribel, which I think are key. One is bandwidth and the other is latency. And very often we've sort of been using bandwidth in order to give us more latency. Or better latency, rather. To give you an example, suppose that you were ordering a meal service and you said, look, I want 52 weeks of food. And your meal service only gave you 4 weeks worth of food, but once a month. Somewhere towards the middle of the month, your food would be stale. Now, you got enough food, but it's stale. So now you would have two choices. Choice one is you would try to engineer your system so that you actually get, one delivery a week, and then you get the same amount of food, but rather than having to throw half of it out halfway through the week, you're actually getting a week by week. Okay, that's what I try to work on with, for instance, network coding and having, much smarter management of the data itself. The other approach, which is the approach to a large extent that we've been taking, is to say, well, why don't you instead increase the amount of food you get? You're going to get 4 different services staggered in time. Sure, you'll get 4 times more food than what you needed. 1 week you get 1 service, 4 baskets of food, another week, another service. And that's in effect what happens with replacing latency with just bandwidth. So a lot of the extra bandwidth that we talk about right now is not necessarily because there is a need for more throughput, more food, if you will. Now, you do need a certain amount of food, right? If you don't get 52 baskets of food, you will run out of food. You won't have enough bandwidth. You won't have enough volume there to sustain your services or sustain yourself. But to a large extent, we have been replacing, in effect, intelligent engineering, which is, getting your food delivered once a week, with just over provisioning, which is getting 4 different services staggered in time. And I think that when you look in particular at the very large amount of bandwidth that has been bought, if you look, for instance, at the latest, FCC auctions for spectrum, you can see that you see these massive demands. And as I said, this doesn't come from phone calls, right? This comes from computing. So what happens with computing, and I think this has a lot to do then with edge computing, is to some extent you're trying to again reduce the latency. And are you going to reduce the latency only by adding more and more bandwidth? Well, at some point, there's also just a question of delay because of proximity. So what do? You cache, you try to make the proximity higher so that you're reducing those delays and, in fact, again, reducing that need for bandwidth. Again, it would be a bit like if you had a food service system and you were ordering your food from very, very far away, you wouldn't get it on time for your next week, right? So you're going to order from a provider that is closer to you, that can deliver your food in the timely fashion. So to me, what happens with edge computing is that it has been interacting to some extent in a very uncoordinated fashion, I would say, to a large extent, with respect to what's happening in the layers that are actually providing the communication, that is to say, providing the transportation. Going back to our example, it's like, you managed to get yourself a provider that was very close to you. You said, great, but then that provider is sending out somebody on a bicycle once a week. Not going to do it, right? So you need all of these pieces to be there. I'll give you 2 concrete examples of of the kind of work that we do. So one example I mentioned network coding is, of course, I've been using examples of food, but, data is algebraic and food generally, I hope, isn't. The difference being that, I can't take an apple and an orange and munch them together. I guess I could puree them, but it's not very attractive. But, that's not what happens with data. I can take, one piece of data, call it X, another piece of data, call it Y. I mean, in the end, I want X, which is my apple. I want Y, which is my orange. But one of the clever things I can do is I can munch them together algebraically. I can sum them, say, do X plus Y. And now I have a much more flexible way to represent my data. So suppose that, for instance, I have a lossy system, which is one of the big issues in particular in wireless systems. And, you're talking about 5G. One of the great things about 5G is that it's looking at developing some fairly underutilized spectrum in the higher frequencies, what we often call millimeter wave, think around 28 gigahertz, so like 10 times higher than the frequencies that we generally use currently, which are usually around like 2.5 gigahertz. And that's great. There's lots and lots of spectrum there, but there are a lot more issues to deal with. It's more unreliable, right? It's a very abundant, but much more tricky resource to use. So now I might be sending you these two pieces of data, and you really need both of them, and you need them quickly, right? So I send you X and I send you Y. And say you lose X and you see Y and say, well, I really need X and Y. This is data. This is not voice where, okay, some part of it went away. I really need all the data. I cannot make a decision. I cannot provide a service if I don't have X and Y. So you say, look, Muriel, I got one of your variables, but I didn't get X. And I said, okay, fine. I'll resend X to you. Okay. This is perfectly reasonable. But that whole time that it took for me to send X, for you to realize that you don't have X, for you to request X back from me, and for me to send it back to you, there's a lot of delay there. There's a lot of, coordination and back and forth around our having to decide that. So now I could say, well, it looks like some of my variables get lost. Maybe I'm going to repeat them. So maybe I repeat X twice and I repeat Y twice. So you get X, then the second X gets lost, and you get Y and Y. So this is great. You got X and Y, but I ended up using twice as many resources, and you got 2 copies of Y. What are you going to do with it, right? You got 2 oranges. You only needed 1 orange. Okay. So that worked, but that wasn't very efficient.
It reminds me a lot about how we were originally talking about the concepts of quality of service and class of service, just in IP in general. So
exactly.
So it's like
exactly that.
So how when you think about it, is how do we advance that? How do we move it forward?
How do we advance that? Exactly. So, X and Y, I mean, everything I told you up until now, they really could have been an apple and an orange, right? That you just tell me, look, I didn't get the apple, I didn't get X, or I didn't get the orange, I didn't get Y, or, I send you 2 apples, 2 oranges, figuring, one of the fruit is going to get lost. But again, now, what if it happens that I said, look, I know that some of the fruit gets lost. She really needs 1 apple and 1 orange. But what I'm going to do is I'm going to do X plus Y. Now, again, I can't do this with apples and oranges, but I can do this with numbers, right? I sum up 2 numbers. It's still a single number. It's still like I sent you 1 piece of fruit. It's a funky piece of, it's a orange apple or apple orange or whatever it is. I send it to you, and, if you have that apple orange, you can subtract an orange or subtract an apple, and you get back the other fruit. So what I'm going to do is I'm going to send you X, I'm going to send you Y, I'm going to send you X plus Y. Now, if you got X and Y, fine, right? If you get X, lose Y, get X plus Y, you can recover Y. If you lost X, get Y, get X plus Y, you can recover X. Okay. So now what I've done is I've sent you 3 pieces of fruit. 1 of them get lost, and you got 2 pieces of fruit. And no matter which one got lost, you're happy, right? And we didn't have to spend that whole time going back and forth trying to identify what thing you lost. I don't also just have to duplicate or triplicate or, however manipulate the fruit, which is really, really wasteful. A lot of it is going to go to waste. So I got the data, what you needed to you quickly. Now, how do we do that in a way which is network ready, right? There's going to be maybe other nodes in between, and some nodes are going to lose the fruit and others are not. I may have multiple paths, basically, I may have particularly go into 5G. 5G is a very heterogeneous suite of technologies. I mentioned the very high frequencies. There's also the same frequencies we use in 4G. There's also frequencies like 600 megahertz that are much lower. That we, many cases we sort of hadn't used for a while, or at least not in these contexts. And so now you're looking, and there's Wi-Fi. Most of the traffic that we think of as 4G is actually Wi-Fi. My phone is usually on Wi-Fi. I have a 5G phone. It's mostly a Wi-Fi phone. It's like my home and my office. It's on Wi-Fi. It's only when I'm going around that it's not. So how do we use all of these resources so that now, again, you don't have to go, well, send me my Apple on Wi-Fi and send me my Orange on millimeter wave. And by the way, if the Apple gets lost, I have to tell you back about it. Oh, wait, you're not on that Wi-Fi anymore. Let me see where you are. Instead of doing that, we're basically coding, which is what these algebraic combinations, I give you the simplest one, which is a summation. We're coding, and then you get a very fluid, very malleable, and highly responsive, adaptable type of system. So that's one example. I can give you another example that we're working on. Right now, I gave you fruit is missing. Sometimes fruit also goes bad. It's there, but you open it, you open the box and you wish that fruit weren't there. It's not looking very good. Those are errors, right? So, what can you do? You can ask for another piece of fruit, but maybe, sometimes it's not so bad. You can just cut off that piece of fruit. Now, I'm not giving your listeners any suggestions. I know it's not good to cut off the bad piece from the fruit, but let's face it, we all do, right? The difference with data is you're not quite sure necessarily where it is. And it also depends on how much of your apple's gone bad, how much are you going to cut off? So that's what we call redundancy. I ended up sending you bigger, juicy apples than what you needed, maybe because that some part may go bad and you may need to chop it off, okay? So how do you do that? Well, in traditional systems, you do that by having codes. And the way these codes work is, again, they're very, very algebraic in nature, as I was describing before. And then there's a lot of back and forth between the sender and the receiver to figure out what codes to use. The receiver has to be, generally equipped with bespoke, highly specialized, highly expensive, often highly energy inefficient hardware to try to decode that particular system. That's to say, imagine that you had a system where you basically have a paring knife, which will only work for honeydew melon or for Granny Smith apples. I mean, it's literally to that level, right? It's for that one, not even that kind of fruit, but that type of fruit, but that particular type of fruit. It's not even for apples. So, it's not even just for low density paired check codes, which are apples. It's for low density paired check codes of a particular type at a particular rate. It's that specific. And the receivers right now have, all these specific knives to try to cut off the bad parts. And generally, also, you end up having to send really huge amounts of fruit. Again, remember the example with all the waste. Basically, we're sending a huge amount of waste. So we know how much of the fruit goes bad. I say, this is called the bit error rate. It's like 1 in 100th of a bit. Okay, so like 0.1% goes bad. And if you look at and that means that normally I would only have to send extra fruit, of about 1/10 of a percent. And instead, what we're doing is we're sending 50% more fruit, 30% more fruit. Again, it's because of an effect. Let's just call it, inefficient engineering, that we're wasting all those resources. And because of that, we need more bandwidth. So a lot of what we work on right now is actually being much more conscious, using optimal codes and decoding them. Now, why weren't optimal codes used up until now? Well, because we had these knives, which, by the way, only let you cut off like an apple in half or a third bit off, or lop off, maybe a fifth of it. It's like right now what we have is a decoder, this item that fixes the errors, removes the bad part of the fruit, and removes it no matter 1% or a tenth of a percent, and for any code. So you have the same knife, whether somebody sent you an apple or an orange or a cantaloupe. You're just using the same knife, and we're actually presenting that. This is work with Professor Duffy at Northeastern University and Professor Yazicic at Boston University. We are presenting this at ISSCC, which is the major circuits conference in February in the Bay Area. So we're very excited, and it's very efficient. Yeah. It's the first one that actually also does below 1 picojoule per bit in terms of energy for the decoding. So it's about an order of magnitude from the state of the art.
So I know Joe's been dying to jump in with a question here.
Sorry, I've been rambling on.
Really, really interesting, because it sounds like, what the work that you and your peers are doing around coding is actually going to improve latency, right? So that sounds pretty interesting to me, because one of the ways that folks had gotten around that in the past is the caching example that you used, and or the over provisioning, right?
That's
that was sort of a way to combat those two things. I want to switch focus here a little bit and talk about wireless APIs. And I think folks are trying to understand how they might matter at the edge. We've lost Muriel.
Apologies, I got disconnected. So I have wireless APIs, and then
yeah, let me. So Muriel, I wanted to talk about wireless APIs and why they might matter to folks as the edge evolves. What are your thoughts?
So, in my view, so let me actually step back and maybe say that I think that defining what an API is also super important. I mean, it's this type of thing that everybody knows what it is, but on the other hand, nobody can quite tell you, right? So like everybody goes, well, of course you want an API. How could you not want some sort of multi-purpose, well-defined, robust way to connect two modules? I don't want an API, said no one ever, right? Although you'd be surprised, I have heard it. But then what does it do, right? And I think what we've seen right now, particularly in the realm of standardization, is we've seen, sort of the APIization, if I may, create a really awful portmanteau, of, let's say, the higher layers. So efforts like Open RAN, are very much in the API domain. What we haven't seen, and this is something I'm pushing very much for, is sort of the APIization at lower layers. Standards have still been, I would say, at the medium access or maybe data link layer and below, extremely monolithic, let's say. Okay, so one example is the error correcting codes that I told you before, right? There's like, if you look at 5G, for instance, there's like two different kinds of codes. There's low density parent check codes, LDPC, and there's CA polar codes, CRC aided polar codes. And that's it. This is a huge wild world of codes. You're going to use those two codes and for a given number of rates, and that's it. That's all you're going to do, and things like LDPCs are very long, and long is usually not very good for low latency. Okay. Now, if you consider the APIization as saying, no, really what I have an API, which is this is my error correcting module, right? Now, you can use the old-fashioned incumbent codes if that's what you want. You can use, so whatever legacy technology you have, you can use new stuff, which is, better suited to your application. It doesn't matter, right? Basically, the API is data goes in, data comes out with a certain measure of reliability out of your system, right? So the chip I mentioned to you, that's called GRAND, by the way, guessing random additive noise decoding, that is exactly, what it does. It just decodes any code, with a moderate or low redundancy. Okay, so having another example is, for instance, we've been doing a lot of work on optimizing modulation. Modulation is how you actually create, say, in the wireless domain, in the electromagnetic spectrum, how you actually create the signals that are going to convey information. Okay. Right now, there's only a certain small number of modulations. If you look at, again, how much performance you're leaving on the table, it's a huge amount of performance. Okay? And if instead of being monolithic through standards that are, in many cases replicating stuff, LDPCs, for instance, fantastic, but they're from the early 60s. Obviously there's been improvements, but, this is inherently pretty old technology, right? Modulations, again, you're doing modulations that are the same ones that I learned when I was a grad student, and that wasn't yesterday. So, how do we actually go beyond that in a system which actually is doing the best thing that you can at every time?
So I know that you've got the sound of your next meeting coming up.
No, I have turned it off. Sorry about that. I thought I turned off the do not disturb.
But if we were going to wrap it up in a sentence, what would you say you're thinking about that people need to do here?
I really like this issue, the modularization, the APIization. I think that really moving away from, making standards define how APIs talk to each other, not defining things that should not be defined, that don't need to be defined, not fixing the codes, the error correcting codes, not fixing the modulation, fixing as little as possible so that you can have the best performance. We are being so staggeringly wasteful right now, and as an engineer, it's just
basically do what matters.
It's
right?
just like
do what matters.
Right, as an engineer,
so
and as a
Muriel,
person. Yeah.
We like to close the podcast with a fun fact. Do you have a fun fact you can share with the audience?
So I'm going to share a fun fact, which is that a lot of people don't know who one of the pioneers in wireless communications was. And her name was Hedy Lamarr. She was an actress, a very successful actress, particularly in the 40s, had a fascinating life. There was a wonderful a movie by Susan Sarandon called Bombshell about her. And I've given a few lectures actually about her patent. Her wireless patent. Much has been written about her artistic career as an actor and quite a polymath. But I think that I don't think that's something people don't know about, but it's maybe an underknown fact.
That's a great fact, and we'll put a link to some of that in the show notes. Muriel, thank you so much for your time.
Thank you both. And if you can send me a link, I will make sure to publicize it in my network.
Thank you so much for taking time with us.
Thank
Have a
you.
lovely rest of your day.
You too. Happy New Year. Bye-bye.
Bye.
Thanks for listening. If you enjoyed the show, please subscribe so you can easily find us again. Follow us on Twitter at Maribel Lopez and at Digital Cloud Gal, and on LinkedIn. Links to our social profiles, show notes, and ways to listen to the podcast can be found at elevatetheedge.com.